So I spoke to Isabel. She has graded your exams, or the exams are graded. They're entered. I believe they'll be returned to you guys in recitations, if I'm not mistaken. Is that what she's done in the past, more or less? Yeah. So she says she'll do it again, and then once everything is done, I'll get the exam grades, and then we'll basically pick up where she left off. And according to the syllabus, she should have covered up until chapter 27, right? Is that right? So she finished chapter 27, so we start from 28. So as far as homework goes, it'll more or less be the same format, except I may not assign as many problems as she does. On the note of homework, I do have one thing I must add. I lectured the same course last summer, and I discovered that a lot of the students have solutions manuals. And that's fine to have solutions manuals and check them, but I must reiterate that you guys shouldn't solely rely on those or look at those until you guys actually attempted and at least gave it a good old college try to solve the problems. Otherwise, you guys are basically just cheating yourselves out of it. I mean, I'm telling you this from personal experience. I was sitting where you guys are sitting, more or less. So let's try to adopt that practice if you guys haven't already done so. Because I can also tell you that the second half of the course will be more difficult. I mean, I'm not going out of my way to make the course more difficult. It's just that the material itself is inherently not as intuitive as the first half, so you will have more trouble grasping the concepts. So it is really important that you guys go through the homework that is assigned and actually do the homework. And I mean, I'm making the homework 10% of the grade just to give you guys enough motivation to do the homework, but it's not worth 50%. So I mean, I don't want everyone, if you don't get a problem, come ask for help, either me, your TAs, or the help desk, and then someone's gonna be able to help you out. And another note, I'm also trying to do things a little bit differently. Like I said, I did lecture this course last year, so I have some feedback from the students. And a couple of the resounding issues were, well, first one was that the lecturer changes halfway through, lecturers, TAs, and all that. And you get used to one teaching style, and then all of a sudden the style changes, material changes, and sort of hard to get used to. Valid concern, and I agree, but unfortunately there's nothing I can do about that, and I think the department can do about that. So the way I approach this to solve that issue is we'll make the first half of the class 50%, second half of the class 50%. And in the end, I'll basically just average the two. And if you look at the point distribution, homework's worth about 10%, labs are worth about another 10%, so 5% for the first half, 5% for the second half. Exams also, I made it so that the finals and the midterms are the same credit. So that again, so that way you have 2 exams in the first half, 2 exams in the second half, and kind of averages out nicely. Second one was that my handwriting is pretty bad. Again, guilty as charged. I can't do anything about that, and I've been writing like it's chicken scratch for as far as I can remember. I got into trouble with my own teachers in my school days, and the way I came across this, or decided to come across this, is to type the notes up. So last year they said, me writing on the board, I write too small or can't write legibly enough, so I started pushing my notes up. So I got complaints that my notes were poorly written. So I'm typing the notes up, and more or less I follow my notes verbatim, right? I mean, I basically write down what I'm thinking when I'm doing these notes, and so these should be a good source. Again, if it's still bothersome, more trouble, what I've decided to do this year was I asked one of the TAs to help me video record the lectures. I'll post them on my website in high definition, so you guys can download them and look at them. But again, I realize that the caveat of this is that people will stop coming to lecture if I post videos and audios. So if I see the attendance go down below a certain threshold, I'll pull the plug on that and no more of that. Right? So sounds fair? All right. So let's go over the syllabus once more, just to make sure we're on the same page. While we're talking about pages, here's my web page. Here's where I'll post all the updates. If you scroll down, you can see the updates from last time I taught the course. This originally was like my blog, but then I just got lazy about making another website and just converted that to the class website. So the URL should be on the syllabus. It's sriteja.physics.tamu.edu. Again, I forgot to introduce myself. My name is Sriteja Upadhyayala, but I go by Teja. So you guys can just call me Teja. That I think is simple enough to remember. All right. So in here you have all the information you need. Material. I know certain tutoring places. I know A+ sort of hoards all the old material, and you guys go there, pay exuberant prices, and get them and sort of memorize the stuff. I don't want you guys to do that, so I'm just making all my old material available, all my old notes, old exams, everything. So the new material will be posted here. So far I posted the notes. So I noticed when I posted notes last year that you have all these websites that just sort of data mine and get all the data. So just to prevent that, I put a password for the notes. It's just Tesla, and here are the notes. So these notes I'll essentially be following down pretty much more or less to the nail. And as I mentioned over there, this is the first iteration. There will be mistakes. So if you find a mistake that I happen to miss, I would really appreciate an email or just let me know what the mistake is, and I'll fix it. Like I said, I'm spending a lot of time on these notes. I also put a little math review for you guys in case you guys are rusty on the vectors, which at this point none of you should be. But just in case, let's fix these problems early. Here's some math review you can go through for vector multiplication, additions, and all that. Then we start with the actual material. And like I said, I'll follow these down to the nail. And here's the syllabus. So we're supposed to start with 28. We'll finish 28 this week. Next week we'll start with induction. So induction is, in my opinion, probably the most important topic in this class, and I mean that powers all our modern industry, so it's fairly important. So syllabus is here. Exam dates are listed. If there's some overwhelming conflict with another class you guys are taking or something, let me know. We'll try to work it out. If you guys want me to move the exam a day here and there, we can also arrange that. But since the date is posted and I need basically full class approval to move exam dates if we need to move it. Of course, I can't move the final date. That's set in stone. But midterm, one or two days here and there, it doesn't make a difference to me. As far as the final, I already got some emails from people who can't take it on time. They want them to take it early, whatever the case may be. Last year also I ran into this issue. Because the class is curved, I can't just give out two different finals, and I have people complaining that one final was easier than the other. So the only way I'll let you take the final early if you have fish camp or whatever it is if you're going into the final in good standing, which basically means, not good, excellent standing. So if I think you'll make an A or a B regardless of what the curve is, then I have no problem letting you take the final early. Obviously it'll be a different version, but we can work something out. So before you guys even email me and ask me about taking the final early, just keep that in mind, and we can go from there. And standard ADA statement, if there's any people with disabilities, just come let me know. We can discuss that. Again, honor code goes without saying, don't cheat. Right? I mean, I don't like, because if someone gets caught for cheating, I have a bunch of paperwork to fill out. So it's my own selfish need to ask you guys not to cheat. I don't want to fill out all the paperwork and go through all that. And so yeah, just don't cheat. Homework, you guys can work in groups. I'm totally okay with that. I mean, like I said, you guys probably all have solutions. So just don't cheat. Any questions? No? Did Isabel do? Yes. It's Tesla. Yeah, Tesla. Nikola Tesla. Well, just Tesla. No capitalizations, everything lowercase. So those are the passwords for the notes. And we'll see how this video thing is working out. If it's helpful, I'll continue doing it. If not, then I mean, like I said, the notes should be good enough, but we can go from there. Any other questions? Did Isabel give quizzes in class? No? Okay. I don't like to either because it's more grading for me. And if there's one thing I absolutely abhor, it's grading. I absolutely hate doing that. And if I give quizzes in class, I can't pawn off that grading onto the TA, so I'd have to do it myself. So I'm not going to give quizzes unless the attendance drops, like I said, below a certain threshold. At which point I'll start giving quizzes because there's like a handful of people. Yeah, I can grade those, no problem. There's 90 some odd people in the class, like the number that's enrolled. I don't want to grade all those. So off the top, I'm not going to give quizzes, but if I see the attendance drop, or if I see homework performance or exam performance go not as well, then I'll start doing quizzes. Your TAs will give quizzes and recitation, or they have been doing that, and I believe they will continue doing that. I'm not setting a minimum or maximum on the number of quizzes. I'm leaving that up to your TAs to decide, but they are required to give you quizzes, and they'll do that. So are we clear on everything? Any questions? Anything at all? Oh, another thing. I know the class is an hour and a half, and it is quite long. I get bored listening to myself talk for that long. So what I propose is we'll go maybe like around halfway through, take a 5-minute break-ish, and then we'll start back up. Does that sound good to everyone? Right. And there may be times I may get carried away or too excited with what I'm talking about. So if we're past that halfway point, you guys feel like you need a break, just interrupt me and say, hey, let's take a break, and we can do that. All right? Everything good? All right, so let's get started. Markers somewhere. Oh, one more thing I forgot to mention. Under contact, you have my email address, and if it's like a real emergency, I have put a widget to call me. And under about, I have a calendar here. So this more or less gives you my schedule. We haven't yet decided on office hours. So any proposals? Once you look at this, I mean, basically besides the lectures on Tuesday, Thursdays, I have meetings here and there, lab work, but any suggestions on what office hours? After class, before class? Tuesday, Thursdays? Tuesday, Thursdays? How about Tuesday, Thursday from 11 to 12? Does that work? Does that work for everyone? Any conflicts? We can do 12 to 1, but if we risk running over, then I now have to run to my meeting, so that if you guys are okay with that, then how about this? Let's do this. Let's go from 11 to 12:30, right? And if we need to stay a little bit longer, we can do that. My office, I have a couple offices. One's on this building, 4th floor, 418. It's one of those bigger offices. I'm either there, or I'll be in the round building, the oval building, same floor, 216. So I'll be in one of those two places. Yeah, 418 of this building, missed is 216. I think I listed it up here. Yeah. So yeah, those are the office hours. Right. So like I said, all the other stuff is listed. So we left off with, or you guys left off with chapter 27. Let's do a little bit of recap on that. So you guys were discussing moving charges, right? And how that creates a magnetic field, right? All right, so we have, and what's the force that moving charge creates? What's it called? It's Q. So if I have, if I'm looking at the force, it's a vector. Oh, another thing I mentioned in there, vectors generally here are written like this, right? I've been used to writing it with an underline. So you may try to switch over to the other format, but if you see an underline for a letter, it's a vector. That's just been my notation. I've had professors that did that, so I got used to that. But I'll try to stay consistent one way or the other, and we'll go from there. So let's do it this way. Force, I have charge, right, Q. times v cross b, right? So velocity of this charge cross the magnetic field it's moving through, right? So we know that moving charge creates a magnetic field, right? So this the force created by that is given by this. So if I look at a point charge with positive q charge, right, and it's moving straight up at velocity v, right, and I'm in a uniform magnetic field that's coming out of the board, which way will the force be? It'll be going this way, right? And that is inherently the property of the cross product. Cross product between two vectors yields a perpendicular vector, right? So this can be perpendicular to both of these vectors, right? And dot product between two vectors gives you a scalar number, right? Right. So this is going to be the force that's dictated by that, and I have this charge, point charge, moving this way. Force is pushing it this way. So at some point, this point charge that started off over here is going to go somewhere here, at which point the force is going to be perpendicular to its motion. So it will create a circular path, right? So in this case, the Lorentz force can change direction when you have a uniform field like that. So this is very similar to the constant circular motion you guys went through in 218, right? So you have centripetal force, it's pushing it outwards, and it creates a circular path. This is very similar to that. So using our old 218 knowledge, we can actually calculate various properties of this, right? Have you guys done all this so far? So it will be a good review. So in this case, if it's completely perpendicular, what is the force going to be? I have a point charge q, velocity e, magnetic field b. What is the force going to be here? So the force here is going to be q, right? The cross product between these two, and if I look at the magnitude of it, it's going to be vb cosine of the angle between them. No, sorry, not cosine, sine. Right? So what's sine of 90? 1. So this essentially gives me q v b. So that is the force that's created by that. And that only happens when I choose v to be perpendicular to b. Right? So that is the force, and given the centripetal force, what's that equal to? mv squared over r. So we know that force equals what? ma, right? So a for circular motion, uniform circular motion, is v squared over r. Therefore, force here is going to be q vb equals m v squared over r. Right? And so it's moving, rotating at a certain radius r here. If you want to solve for that radius, well, we don't know the radius here, so we just isolate it and solve for it. So it's going to be, radius is going to be m v squared over q v b. Right? Good. So again, mv here is the momentum of the particle. So it's fairly logical if you think about it, because if you have a bigger charge, then the corresponding Lorentz force will be quite large. Right? So if the Lorentz force is really high, so the charge is really high and the Lorentz force is high, then it stands to reason that the radius will be small. So it's basically pushing it to a smaller circle. Right? Does it make sense? Okay. So again, if we look at this again, if I have this point charge with a higher mass, if it's really massive, it's harder to move it or change its path. So you'll have, the mass is higher, you'll have a bigger radius. So another logical thing there. All right, so enough with this review. Let's start with Biot Savart Law. So let's consider a wire. right? And let's consider some current I going through this wire. Now, if you look at the magnetic field in the vicinity of this wire, we know from experiments that have been conducted in the past that it is, in fact, circular, right? So it sort of curls. If I have current going this way, again, right-hand rule applies. Current's going this way, you curl your hands around or your fingers around it. So that's the direction of motion, and it's circular, and it decreases as the distance, the radius goes forward. Again, so you'll have magnetic field, something like this, right, going all around, and it's going to be inversely proportional to R. So it's going to be magnetic field is going to be proportional to 1 over R, right? So, and by convention, again, this is just convention, the direction of this field is dictated by the right-hand rule again, right-hand corkscrew. So if my current is going this way, my magnetic field is going to be traveling around this way. So I put arrows in like that, right? Again, that's just by convention. Someone a long time ago said, okay, let's just use the right-hand convention for this, and start doing that. You've seen something similar with electric fields, right? Electric charges. So this is sort of similar to that. Now, if you have a wire with uniformly distributed charges, you can also see that the electric fields in the vicinity fall off as 1 over R. So the electric fields also share the 1 over R, the inverse relationship, right? The reason for this is that you have electric monopoles. Right? So if I have a single uniform point charge, I can look at the the electric field due to that. So, but for magnetic field, I don't exactly have a monopole, right? I have to have a dipole. So we'll get to that. So this is the reason for electric monopoles, the fields actually fall off as 1 over R squared, right? So electric field follows the inverse square law principle, and then the magnetic field here follows the just inverse principle. So when I integrate over a straight wire, we get the 1 over R term. So by analogy, it's possible that if you look at magnetic monopoles, we can also get the 1 over R squared term. But like I said, we don't have magnetic monopoles. In theory, they can exist, but no one's discovered them. So once someone discovers them, they can get the Nobel Prize, and then we can close the book on this and move on to something better. So the simple fact here is that magnetic fields fall off as 1 over R. So if we were to carve up a wire into small elements, your DL elements, right, and you were to look at the contribution due to those things will also fall off as 1 over R squared. So when we integrate that 1 over R squared, then we get the 1 over R for the whole wire, right? So this precise formalism is what Biot Savart Law is all about. So we have to introduce little DL elements, and then we have the current, and then we look at the differential contribution dB. So from this, we can say dB, the differential small magnetic field, is going to be some proportionality constant C. We don't know what that is. We'll figure that out, times the current times dl cross r hat vector over r squared, right? So this is more or less what the Biot Savart law will look like. And C over there is just some proportionality constant that we'll discover, or not discover, but get to in a bit. You had something similar with the electric field. You had the 1 over 4 pi epsilon naught, right, for the constant in the front. You call that K. You'll have something similar here for this. So this C was initially looked at experimentally, and it was discovered to be along the order of 10 to the negative 7, right? 10 to the negative 7 coulomb, wait, in SI units. So there's no units for this yet, but it's in some SI units. So for the C, we write it as mu naught over 4 pi, where mu naught is the permeability of free space. And for Coulomb's law, you had what the 1 over 4 pi epsilon naught for Coulomb's law, and that is approximately 9 times 10 to the 9. Right? So given this, I can erase the C and write mu naught over 4 pi. And we're done with that. So now we can apply Biot Savart law to calculate magnetic field. So again, let's look at the straight wire. So if I have another straight wire, let's give it a length of 2a. So here's my origin. I go from negative a to a up here, right? I'm looking at some small element dl here. I want to calculate the magnetic field some distance out, let's say over here, right? So this is some distance x that we don't know, right? So this is going to be, well, this is x, this is going to be y here, right? We don't know that distance yet. So this is going to be r. We know that's going to be equal to x squared plus y squared square root. And this is going to be my r hat vector because I'm looking in that direction. And so we need to first look at what, write down what dB is, then we integrate and find out what B is. So dl here, now I can basically write that it's dy, right? I'm integrating over that, so it's dy. So I can write that and basically replace dl with dy in the integral. Another thing, I have to write down what my angles are. So I'm going to say that this is angle phi, right? So this is going to be pi minus phi, right? So now I can say that sine of phi is equal to x over square root of x squared plus y squared. And I go from there. So now I can move on to actually writing what the integral is. So I have dB, right, equals, from what I have up there, mu naught over 4 pi integral, sorry, not integral yet, I times dl cross r over r squared. So dl is going along this side, r hat is this way. So basically this thing boils down to dl. R hat is just a unit vector, so I won't have anything there. Sine of phi. So dB is going to be mu naught over 4 pi times I, dl, which I'm saying is dy, sine of phi, which is going to be x over square root of x squared plus y squared. Right? Okay. So now I have to substitute in for dy, and oh yeah, so I forgot the r squared here. So I have times 1 over r squared. R is that, so I get x squared plus y squared. Right? So from here, I simply integrate both sides. I get b equals mu naught. I is a constant. I can bring that out over 4 pi integral. So I'm integrating from negative a to a. Right? So I can just leave that as my integral. Negative a to a integral of x over square root of x squared plus y squared times dy over x squared plus y squared. Mm-hmm. Would sine phi be what? Yes. Yeah, it would be. Well, let's do this. Let's in that case we can just integrate. Yeah, we can just replace this with dx. That'll solve the problem. Sine phi. No, I think this is correct. Did I make a mistake in writing it down? Yeah, but this is my, oh yeah, so I guess you're right. So this is going to be 90, so it's going to be theta. Just a second, let me look at the diagram again. Saying this changes to phi here. Yeah, I mean that's pretty much it. So this is phi. Yeah. Oh, all right. Well, so if I make this phi, and the other one. This is phi, and they're saying this is pi minus phi. Yeah, but then I have to look at the sine of 90 minus phi then, which is just a cofunction identity, so it should be the same. Yeah, all right, that works. Does it? Yes. Yeah, that works. All right, thank you. All right, so from here, you have the, the integral is a bit complicated. I don't expect you to do something like this on the exam. If I do, I'll give you what one of those integral tables or what the form would look like, and you would carry out the integral from there. But let's, for the sake of exercise, go through that integral. So what I would end up with here, from there I can multiply the denominator, so I would get b equals mu naught I over 4 pi integral of negative a to a x, well in that case that would be dx over there, I'll just change that to dx over x squared plus y squared to the 3 halves. So now I do a trig substitution, so I'll say let y equals x tangent theta, which means that dy, sorry, this will be dx here still, dy is going to be equal to x secant squared theta d theta. Right, so from here, substitute that in there, so I get mu naught I over 4 pi integral of secant squared theta over x times 1 plus tangent squared theta to the 3 halves. So this is going to be equal to mu naught I over 4 pi square root of secant, integral of secant squared theta over, this is going to be 1 plus tangent squared theta is going to be secant squared, and then square root of that is going to give me secant times that is going to give me x secant cubed theta. Right, so secant squared goes away, this goes away, so I get mu naught I over 4 pi integral of cosine theta over x. Then I have to substitute back in for, if I integrate this and I substitute back in. So once I integrate cosine, I get, theta. Right, so I get this equals to mu naught I over 4 pi times 1 over x sine theta, and then I substitute back in where sine theta equals y over square root of x squared plus y squared. So therefore I get mu naught I over 4 pi y over x square root of x squared plus y squared. And I go from my regular limits, negative a to a. Right, so this equals to mu naught I over 4 pi. Once all the math is said and done, I get 2a over x square root of x squared plus a squared. So from here I can conclude that the magnetic field is mu naught I over 4 pi times 2a over square root of x over square root of x squared plus a squared. All right, so this is the magnetic field that I end up with. So now we took a finite length of wire and calculated the magnetic field for that, right? Now what if we were to approximate the magnetic field for an infinite length, or a really, really large wire? What would we do? So we have the length over there as a, or negative a to a, right? So let's say we say that a is so large it approaches infinity, right? So what do we do then? Look at this. These two are basically our a terms. So if a is really large over there, basically x squared plus a squared is simply going to be just a squared, right? So a is so large that x doesn't matter anymore. So especially a squared is so large that x squared doesn't matter anymore. So what I end up with essentially is 2a over essentially a over there, right, times x. So basically this we can cancel out. So what I end up getting is, in this case, when we approximate this to be really large, that thing just simply goes to a. So we get, and if we're looking at a distance r away, what we end up getting here is b equals, the top part remains the same, mu naught I over 4 pi, right? And we have a 2 there, so the 2 cancels out. With this I get a 2, and then I have this x, which I'm saying is r distance away, so this is r. I get, that is my answer. So basically the magnetic field here falls off as 1 over r, right? It's falls off inversely, or inversely proportional. So again, this r term is quite relevant here. So let's look at an example to give you an idea of what the units and the numbers look like for this. So if I'm looking at some distance where r is 0.1 meters away, right? And the current I'm looking at is 100 amperes. So if we plug, basically from this equation, we know mu naught is, it's a fundamental constant. We know what obviously 2 pi is approximately 6 point something or other. What we end up with is B equals 2 times 10 to the 4th Tesla. You guys already went over the units for magnetic fields, right? It's Tesla. Right. So again, one more thing on exams. One thing I'm really picky about are units. So not necessarily units, but the dimensions. So if you're looking at magnetic field, now I expect you guys to end up with Tesla. Right? If you're looking at forces, I expect you guys to end up with something to the equivalent of newtons. Right? So if you guys have the right units all the way through the end, then the chances are your answers are correct. And if your answer is not correct, I may give you guys some points for carrying the units all the way through. But if your dimensions don't match up, then I can't show any leniency there. So just to yes.
Do you want us to show units all the way through our work, or just?
So the way I've always put my exams is there are no numbers, so they're all going to be in terms of variables. So there's no need to have calculators or anything. There will be no numbers on the exam. So everything will be a variable. So you need to essentially have a right combination of variables there. So for instance, if I'm looking at a magnetic field, obviously I expect to have the mu naught over 2 pi there, but I also expect it to be something to the effect of I over R, right? Some current amperes over distance, and that's essentially equivalent to Tesla. But right, I expect you guys to have the right dimensions there. So yeah. So I mean, numbers because I've graded exams too many times, and that's why I hate it. When you have numbers, you can plug into the calculator and make some mistake, and then the grader has hundreds of exams to go through. He doesn't have the patience, he or she doesn't have the patience to go through and find out where the mistake was made, so you'll end up getting the whole thing wrong. So just to avoid all that, I don't deal with numbers here. I mean, on the homeworks, you guys will have numbers, and the way you should actually also solve on the homeworks is go through it all in the most general terms possible, which is basically in terms of variables. You say, okay, you're given a current of I is 50 amperes. Say, okay, current is I, radius is R, and go through, solve for it, and in the end, plug in the numbers, and that'll make your life a lot easier. I mean, this is second semester you guys are doing this, so I'm sure most of you guys already have adopted these practices, right? Otherwise, it's kind of hard to survive this far out. But all right, so once we plug in, we get 2 times 10 to the 4 Tesla. So this is approximately 2 Gauss, right? Again, Tesla is interesting. You have this is equal to Webers per meter squared. And one of my very, I guess, irrational hobbies, if you will, is I collect various coins, currencies, and all that. And Tesla had Serbian ancestry, right? So his ancestors are from Serbia. So on the Serbian 100 dinar banknote, you have a picture of Tesla, and on the back it says Tesla T equals Webers per meter squared. So I mean, if I asked you the question, what is Tesla in terms of Webers, now you can think back to the Serbian banknote. So to put things in perspective, so if I have 100 amperes, so what's a normal vacuum cleaner? A normal vacuum cleaner runs about between 10 and 12 amps, right? That's the current it goes through. So 100 amperes, let's say it's an order of magnitude more. I'm running 10 vacuum cleaners at a time. So if the wires aren't shielded, I'm running all that current at once, and I'm looking at 0.1 meter away. I'm looking at a magnetic field of 2 Gauss. When the Earth's inherent magnetic field is, does anyone know what it is? Close. Well, it's half of that. It's half a Gauss, right? So the Earth's magnetic field is approximately half a Gauss. Now, if we take R, this R to be, instead of 0.1 meter, if we take it to be 10 times larger, 1 meter, right? What would my magnetic field be because of that? If r is 10 times larger, what would b be? 10 times smaller. So I would expect this to be an order of magnitude smaller, and this would be 0.2 Gauss. Right? So already, once we're about a meter out, the Earth's magnetic field starts to dominate. Right? So I mean, you realize it's not that much of a profound magnetic field it produces, but it's still, when you're close by, it's a considerable amount. So it's nice that we can see the 1 over r term come out of this, and it's also been proven experimentally that it does fall off as a factor of 1 over r. And in fact, this principle of inverse square law and inverse laws go all the way back to Isaac Newton, when he actually first suggested that the Earth's gravitational field falls off as 1 over r. Sorry, 1 over r squared. So you guys from mechanics remember the whole big formula, right? So you have force equals some big gravitational constant, m1, m2 over r squared. So he was the first one to suggest that the field over there falls off as 1 over r squared. And later, from Newton, it became a logical extension to apply that to electric field. And we said, okay, the electric field falls off as 1 over r squared. And that would also have been true if we were dealing with magnetic monopoles. We would also have seen 1 over r squared decline. But like I said, we don't have magnetic monopoles experimentally, and theoretically they say it could exist, but no one's ever found them. So we end up with 1 over r here for dipoles, and that's essentially the idea behind the Biot Savart formalism. And there's basically Biot and Savart are two French people that worked together and came up with this. Now we calculated the magnetic field of a straight line. Let's calculate the magnetic field of a loop using Biot Savart law. All right, so let's take a current carrying loop. Right? And this has the current going around counterclockwise. So let's say current is going this way. So which way would the magnetic field point? Out of the board? No, it's so the plane is, so this is my plane. It's going around this way. It'll be going up, right? So if you think about it, so this let's take a small piece of wire here, right? So this small piece, current's going this way, so I curl up, so this point is going to come up, right? And if I do that all the way through, you'll see that the magnetic field aggregate is going up. So I mean, I think that's what whoever mentioned it's going out of the board meant, right? So I mean, but basically, I'm looking at an oblique plane there. Another thing you'll notice on the board is my handwriting. In addition to my crappy handwriting, is my drawings are also horrible. So when I type up the notes, I either steal the pictures from the book. If I can't find them, I make my own with the proper circle tools and all that, so it's nicer. But sometimes I can't find the proper tool for loops and stuff, so you'll see really atrocious loops and all that. But yeah, all right. So here's we have that. It's at some radius r, and let's take some small integral element dl here. And it's basically we're breaking it up into small dl elements. All right. So again, we have to determine the magnetic field here. So magnetic field, I would have to integrate over what? So for the previous one, I integrated over the length of the wire. For this, I would have to basically, right? So I basically integrate over the loop. So B is going to be integral of the loop, right? And we're looking at integral of dB. So this is going to be equal to mu naught over 4 pi I over r squared, because r is also a constant, integral dl cross r hat. So dl and r hat are always, well, first of all, dl and r are always at any given point perpendicular, right? You can agree with that. So if I have r here, dl at that particular point is like that, so it's perpendicular to r, right? And that applies everywhere you're looking at it. So basically r is the radial direction going, let's say, inward, right? Yes? Okay, so it's basically, so dl cross r hat, that's my radial direction, it's simply going to be dl, right? Okay, so again, if you want, we can do that a bit more rigorously. So I get dl r hat, which is 1, sine of the angle between them, which is pi halves. So this is simply going to be equal to dl. So from this, I get mu naught over 4 pi. dl is the whole loop, right? So that's going to be what? When I integrate over dl, I get 2 pi, right? So I would get I over r squared times 2 pi r. So this is going to give me, r goes away, so I get mu naught 2 pi times mu naught I over 4 pi. Wait, let's cancel this and just have a 2 here, 2r. Right? So this is the magnetic field for a loop. Right? Makes sense? So once you do a problem, it's more or less garden variety, just keep applying it to different situations. We'll introduce complications as we go along, but more or less that's the idea. All right, so we have the magnetic field of a loop, we get mu naught I over 2r. So let's look at the same numbers that we looked over over there. So if I is 100 amperes over here, and r we're looking at initially is 0.1 meters, in this case, you also get magnetic field to be something approximately 6 times 10 to the negative 4th Tesla, right? So it's about 6 Gauss. Approximately. So again, this is just an example to show you how easy it is to calculate using Biot Savart law the magnetic field at the center. So we can do another one off center. So this is right at the middle. Let's do another one where we sort of move it off axis a little bit. Not actually off axis, but in the center, but moved along a little bit. So all right, so let's look at something where I have some loop, right? Here's one of the axes. Another one is here. Another one comes out, right? So this loop is along the back plane there. And let's say this is my x-axis, and this is my y-axis, and this is my z-axis, right? So current is going in this way and coming out this way, right? Going into the bottom, coming out of the top. Now, again, the the loop lies in the YZ plane, how does the magnetic field look like with this? It's coming along the x-axis, right? It's going to be like something coming out of here. Well, not off-axis, but no, basically something like that, right? So again, let's take some small differential element, dl, going this way. That's my dl. I is going to be flowing in this way. And so I'm looking at it from this dl element to this point. This is going to be my, let's call this my theta. This is my 90 degrees. This is going to be 90 minus theta. And then of course my dB is dBx is along this way, dBy would be along this way, right? So, and basically using that you can calculate this, not entirely difficult, but however, if I were to shift this from the center to somewhere off axis, it's virtually impossible to calculate. I mean, you could do something called off-axis extrapolation and eventually calculate that, but it is far beyond the scope of this class. I should just learn that last year in my graduate level equivalent of this class. So it's completely off or beyond the scope of this class, so don't worry about it. So therefore, you don't have to worry about getting a problem where you're looking at it off axis on an exam. So let's look at magnetic field lines once more. So for this, how is the magnetic field going to look like? So if I have current coming out of one place and it's going to go in another place, now if it's coming out, it's going to have something that goes like that in this direction, right? And then for this, it's the opposing direction. And it's going to be going up. And of course, you have the divergent lines here, divergent lines there. So this is more or less what you would expect from magnetic fields, right? So this is sort of similar to the field lines produced by electric dipoles. This is a magnetic dipole we're looking at. If you have an electric dipole, it's something similar. If I have a negative charge here and a positive charge here, I would have lines basically going from here to there, right? And then basically coming out like that, right? And basically every variation of it. But if you're very far away from the current loop, the magnetic field configuration will look sort of similar to what you see with the electric field. And this has to also do with the flux and the closed line integrals of that. So we'll get to that in a second. So we know what does Gauss's law dictate here for electric fields? What is Gauss's law? We have integral closed or open? Closed of E dot dA equals charge enclosed or epsilon naught, right? So if I have a let's say even for the electric field, I have a positive and negative, and I'm looking at my Gaussian surface that encompasses both the charges. So I'm looking at these two are my charges enclosed, right? So what's my electric field? What's my charge enclosed going to be there? 0, right? Because I have plus q and minus q, they add up, I get 0. Same exact thing with the magnetic field. Magnetic field, if I have a closed loop integral B dot dA, I get 0, right? Doesn't matter what you're looking at, because if you have a magnetic field, it's automatically assumed that it is at least a dipole, or it is a dipole. You have both poles, right? So if I'm looking at some bar magnet, let's say, right, this is plus or north and south, right? So if I'm looking at my Gaussian surface that encompasses both of them, whatever field lines that go out of here come back there, right? So the net result is always 0. So this equation is known as Gauss's law for magnetism. So remember, when you're looking at flux of through a surface for magnetic field, if the surface is closed, the net flux is always 0 for magnetic fields. So this is one of the 4 Maxwell's equations. So far you guys did Gauss's law for electricity, right? This one, right? Now you guys did that. So there you go. That's another milestone in the class. So you guys have, I'm sure, heard or read about this, right? You have 4 equations that are known as Maxwell equations. Yes, more or less heard about it? All right, so I'm telling you now, there are 4 equations known as the Maxwell equations. And with those 4 equations, if you understand them thoroughly enough, you understand the entire class, right? I mean, that basically governs the entire class. So another thing is I won't be giving you those 4 equations on the exams. So I expect you guys to know them. And we only introduced 2 of them so far. We'll get to the other 2 and all the corrections for them, throughout the class. But make sure you know them. I told my class last year the same thing. Know them. I won't give them on the exam. And I told them I may even put them as simple fill out Maxwell equations here on the exam as a question. And they didn't listen to me. I put that question on there, and half the class got zeros on that problem. So another word of wisdom. If I mention exams, I'm not out to get you guys. I'm trying to give out information to make sure you guys do well. So just listen up. All right. Should we take a break for 5 minutes? Some people are sleeping already. All right, let's take a 5 minutes and we'll meet back here. Because it's produced by in the both xy plane, has some magnitude of dB here. All right, some vector in some direction. So we know that the dl, this dl, and the r hat vector are again perpendicular, right? So they're perpendicular, so the cross product between them just yields dl. So we get dB equals mu naught I over 4 pi times dl over r squared, right? So again, this equals to mu naught I over 4 pi dl over x squared plus a squared. Right, so I'm some distance x away, and a is the that distance up there. So you have that distance up there, the hypotenuse of that. So if we were looking at one of the components of this, so I told you this thing breaks down into dbx and dby, right? So we want to look at the components, respective components of that. So we know that dbx is simply db cosine theta, right? And then dby is going to be cosine sine theta. So over here I have this is going to be equal to mu naught I over 4 pi dl over x squared plus a squared times cosine theta here is going to be a over x squared plus a squared to the 1/2, right? dby, the y component of the magnetic field, is going to be something similar, equals mu naught I over 4 pi dl over x squared plus a squared times instead of ax here I'll have x over x squared plus a squared to the 1/2. And I'm going to say that this equals to 0. Anyone know why? So, sorry, someone was going to answer? Exactly. So when you go around, the y components from the other side, they cancel out with the ones on the top. So that goes to 0. So we're only left with the x component of this, really. And okay, so let's integrate that. So I'm going to continue working over here. So bx, right, is going to be equal to mu naught I over 4 pi integral, I can pull out the a, dl over x squared plus a squared to the 3 halves. I can actually also pull this whole thing out, so I get a over x squared plus a squared to the 3 halves integral of dl. Right? So again, when I integrate dl, if I'm in radial components, what do I get? dl, I'm integrating dl, which is basically going all around. What's that? Yeah, so basically I'm obviously dl is going to be 2 pi a, right? So I mean I can in principle break this up into dl, which is just going to be whatever that a is, times theta going from 0 to 2 pi. So basically this thing boils down to 2 pi a. So bx, or the magnetic field, is going to be mu naught I a squared over 2 pi's cancel out, so I get x squared plus a squared to the 3 halves, right? And this is on the axis of the of that loop. Again, as I said, if you're looking at something that's off axis, it's virtually impossible to calculate. Now we looked at one loop, right? So now the next logical progression is we look at multiple loops. So what's going to happen with multiple loops, do you think? Multiply by n. So let's say I'm giving you n number of loops, right, stacked next to each other. Basically, you just multiply this by n, so it basically becomes n times that. So I get n times that will give me the number of loops, right?
For that, you have to assume that x is bigger than the thickness of the loops. Is that because if you have a bunch of loops that are stacked on each other, is that what you're trying to say?
Yeah.
So then you have to say x is a lot bigger than the thickness of a loop, right? Or I guess, or does the ones does that make sense?
The thickness of this actual loop.
Yeah.
I mean, we're assuming sort of idealizing the conditions for this. We're assuming they're like really thin wires with no resistance. So yeah, I mean that assumption is given. Once you go into the thickness of that, then the axis. No, it's not that the axis changes, but once you have really thick wires, you can actually have magnetic fields inside those wires, right? So then those have to be calculated and all that. So as of now, this is just a simple current carrying conductor. We're not looking at it inside the wire, so assuming they're really thin or negligible thickness. So next, when we talk about Ampere's law, we'll have the ability to calculate the field inside and outside conductors, at which point we sort of have to subtly hint at that distinction. But as of now, it's just really thin wire. So, right, makes sense? Right. And also, you can start making plots about the distance and all that. So if I'm looking at the magnetic field strength over here, ideally, this is like the x distance away. You would have something like this, right? You have like negative 3a, 0, a, and this is the maximum point, right? So basically, in the middle of this, of the loops, is where you'll get the maximum amount of magnetic field strength. So that also sort of follows logically. All right, how much time? All right, so we have 10 more minutes. We can introduce the next topic, which is Ampere's law, and we'll finish that up on Friday. So Ampere's law is actually quite quite an interesting one. So originally, magnetism and all that, it was given that name because people noticed that they saw two minerals, more or less, attracted to each other, right? And this was discovered in the ancient cities of Magnesia, apparently. So that's why it got the name magnetism or magnets. And initially, this was thought to be completely different from electricity, right? But now we know that these two are completely inherently related, right? You have current flowing through that can induce a magnetic field, vice versa, we'll learn later. And so in 1819, Austrian guy, I believe, and Oersted accidentally discovered that electric current causes the compass needle to sort of shift. So he discovered that current can actually produce magnetic field, and that's how the whole thing came about. So, and again, right now, as of now, we look at steady state currents, so we look at magnetostatics, so we're looking at sort of just magnetic fields that are staying still. We're not looking at changing magnetic fields or anything yet. So in the previous section, we looked at Biot Savart Law, right? That basically looked at some cross product to get the magnetic field and all that. So we'll sort of try to simplify that a little bit, or at least it'll seem simpler in the beginning. Because let's be honest, you take any one of these topics, you can come up with some really crazy problems that are not so simple. But before we even move on, I have to say you have Ampere's law, which you can use to calculate magnetic fields, and you have Biot Savart law, which you can use to calculate magnetic fields. So the question inevitably will arise later: which one do I use for so and so problem, right? So that depends. Now, if Ampere's law is sort of like Gauss's law, and I'm losing that term really loosely. It's similar in that if you have symmetry, you can easily exploit that symmetry and get to that answer in a matter of a couple of seconds, a couple of steps, right? Something you can do with Gauss's law for calculating electric fields. But as for for Biot Savart law, you have to go through the whole formalism, look at the cross product, integrate, and all that. So it can be a bit more complicated. So again, if you're looking at the current going through a wire like we did before for Biot Savart law, right? But let's look at the cross section of it. So if I have the current going through this way, it's going in this way, right? My magnetic field, right, is going to be something like that. So at this point, my magnetic field is going to be coming down this way. At this point, magnetic field is going to be somewhere up there, right? And again, this is some radius r. And we also looked and calculated this before, and we said that the magnetic field here is mu naught I over 2 pi r. Right? So now again, if we carve this up into little dl elements, right? And we take the closed loop integral of this. So if we're looking at a closed loop integral of B dot dl, so magnetic field that's perpendicular, and you have all the dl elements, what do we get here? So B is tangential to the actual circle, right? So dl elements are actually just part of that circle. So at any given point, magnetic field is always parallel. It's in the same plane as the dl elements, right? So cross product between two vectors, the magnitude can be given by b dl cosine theta. Cosine of 0 is 1, right? So basically this boils down to integral of b dl. So this is going to be dl going around. I get b times 2 pi r, right? Okay, and if we substitute this, what we got, into this, we can end up with, well, this is going to be equal to mu naught I, right? Because if I multiply both sides by 2 pi r here, I get 2 pi r b equals mu naught I, right? So I can set this equal to mu naught I. So again, since b is inversely proportional to r, regardless of whatever value we choose for r, you always end up with mu naught I, right? And it was Ampere who first suggested that you don't have to go around in an actual circle to get that same result. You could have any kind of contorted shape. So you could have whatever shape, and here's my magnetic field, my current going in, and then at some point here, some distance away, I have some dl here, and then some B field over here pointing out, right? And you can still come up with that as long as it's a closed path, as long as whatever path I'm taking is closed. For whatever surface I have, I can calculate the magnetic field. So what we end up with here is integral of B dot dl equals mu naught, and that's the current that's enclosed in there, right? So times I enclosed. Right, sort of similar to Gauss's law, but there are some subtleties that differ. So this right here is what we'll call Ampere's law. I mean, later on we'll introduce something called Maxwell's correction, but that's a few weeks down the road for us. So this is enclosed. This is sort of important. So this has to be enclosed in whatever surface you're looking at, and using this is actually quite easy to prove the Biot Savart formalism. And basically, we can take the same examples we did there, and then show that the results we get for the magnetic fields will be the same. Right. So the direction of our traveling sort of also matters. So if I have let's flip the direction of this. So if I have something that's going out of the board, right, my B fields will change direction, right? So if it's coming out of the board, my magnetic field is going to be in this way, and it's going to be in this way, right? So by convention, we're going to say, okay, the integral of that, B dot dl, is going to be equal to mu naught I. Right? Assuming that my dl is in the same direction, my dl is going this way, dl is going this way. Right? If we switch the direction of what my dl is going to be, so my dl is actually going in the opposing direction, right? What is this going to be then? Negative, because cosine of 180 is -1. So I get a negative there. And for instance, if I have a current here, or wire current coming out of here, and this is the path I choose, right? This at some point is going to have some magnetic field, right? And let's say this my dl also is going in this direction. What's my integral of B dot dl going to be? 0. Right? Because my current is not enclosed. I don't have any current in there. So my B dot dl there is going to be 0. So, I mean, we can also choose some very strange closed paths. So right now we're looking at this normal plane, right? But let's say I take so, like I said, it can be any contorted closed surface. Normally it can be a plane, or you can think of it as a bag you attach to it, right? Or another way to think about it is, those soap bubble maker things. So you take that thing, dip it in soap, pull it out. You'll have some sort of shape that comes out. So as long as that the surface here is closed, you're fine. So, for instance, if I have a certain current coming in this way, right, it goes in there, comes out of there. Let's call this I1. Another one that comes in this way, right? This is I2, right? So what's going to happen here? I have two currents. When I do my whole B dot dl thing, what do? Basically, yeah. So as long as the surface is properly defined, you can have these two currents defined however you want, as long as I1 is less than 0, I2 has to be greater than 0, and in principle, you can do the B dot dl and have the same thing. So basically, it's like you have two wires, but yeah. So again, any loop is fine as long as you close the surface. Your loop path is closed, and you have a attached surface that's open, and then the loop is closed. You can integrate over it and then attach any I enclosed and get the answer. So I mentioned earlier that using Ampere's law, you can calculate the field inside a conductor, right, inside a wire. So far, actually we're out of time, so we'll save that for next time. So preview to come.